A combination is different from a permutation in that this time, while we still can't have any repeats, order doesn't matter. We're not really caring about the order there. So the quick notation for finding a combination or finding the number of combinations of n elements taken r at a time, this time is n choose r. We saw this previously when we were coming up with the coefficients of our binomial expansion, which was the same values that we got from looking at Pascal's triangle. So we should be somewhat familiar with this. So again, n choose r here is going to come up with the number of combinations. And just like I said in the previous video, let's jump into a problem. So let's look at this first one. How many ways can 5 basketball players be picked as starters from a team of 20 players that are available to us? Now, this is a bit different from a permutation because unlike the officer problem, where once one player was put in a specific spot, then it rules out that player from playing from being in another officer position. If you're thinking back to the officer problem with the clubs, this time we have what we would say 20 choose 5, which I can write that way. I can also write it as 20 choose 5. And what this looks like here would be then the following. We've got 20 players to choose from. I've got 5 players that I need to pick, and then I need to find the difference of 20 and 5, which would be 15 factorial, right? Which would then give us this many possible lineups. And again, I want to make sure that we're able to compare this to the club officer problem where order doesn't matter. It doesn't really matter which player is playing which position here. We just need to be able to choose any 5 players from the group of 20 that are available. Okay? Let's look at another problem. Now, in this problem, we're going to find the number of diagonals in a hexagon. Now, at first glance, we might be thinking, wait, how is this a combination problem? And maybe let's think about a way of rephrasing this. So first off, let me actually go ahead and just quickly sketch a hexagon. It's not going to be a fantastic hexagon. I'm just going to apologize in advance for my shoddy hexagon here. And let's say we just have something like this. Not great, but you get the idea. I'm going to just erase that. All right. So let's say we have something like this. All right. A hexagon here. All right. So for this problem here, we're going to go ahead and we're just going to label our different vertices so we know what we're setting up. Okay. Now, if we're trying to find the number of diagonals in this hexagon, what we're effectively referring to is this is the set of diagonals that can be drawn from vertex A. Now, if I select vertex B, I'm looking at the number of diagonals I can draw from B, which would give me this, and this. And we could keep going around. And obviously, this is a problem that we could do by just drawing all the diagonals and just keeping track of them. Another way of thinking about this is to ask ourselves the question, how many pairs can be made from 6 vertices? So how many pairs can be made from 6 vertices? And I'm sure you've seen versions of this problem in the past where if you had 6 people standing in a circle, for example, how many handshakes could there be between those 6 people standing in a circle? That's pretty similar to this, but not quite exactly. Because if you're doing a handshake, you could shake the hand of someone directly next to you, but that's going to be different from this problem here where you are looking at a diagonal. So you drawing a connection from A to B, for example, while that would be a handshake, it isn't quite a diagonal. But there's a reason why I'm bringing this up. Because I think the most efficient way of going about this problem is to first come up with the total number of connections that you can make to actually do that handshake problem. What are the total number of connections you can make? Let me actually write that out. The total number of connections. So in other words, this time we would count A going to B, A going to C, AD, AE, AF. So we're going to include both the sides and the diagonals. And what would that combination look like? Well, that would be 6 vertices to choose from, and we're going to choose any 2 at a time. Any connection is a link between 2 vertices. So this would be 6 choose 2. So really quickly, that would be 6 factorial over 2 factorial times 4 factorial. And if you can just do that quickly mentally, you should see that it's 6 times 5 divided by 2 factorial, which should just give us 15. So there's 15 total connections, 15 total line segments we can draw from any 2 vertices. Now from that, let's go ahead and let's subtract the total number of diagonals. The total number of diagonals. Okay, oh, excuse me. The total number of diagonals is going to be the total number of connections. This, I apologize. So let me actually just rewrite this. I got a little ahead of myself. I was getting kind of excited about arriving at the solution. Our diagonals then would have to be the total number of connections that we just found, right? So let me actually just write that again. The total number of connections that we just found. And then from that, subtracting the total number of sides. So just kind of pause and think about that for a second. If we take the total number of connections and then just subtract the number of sides that we have, then boom, we're left with the total number of diagonals. And we don't have to really do much to figure out the number of sides. This is a hexagon. How many sides are in a hexagon? You should know that that's 6. So if we would just say, and let me just write this in purple, we would say that this would be the 15 connections total minus the 6 sides. And so this would be 9 diagonals, right? So again, could you have done this problem just by drawing the diagonals? Yes. But what if we had a polygon with many more sides or many more possible diagonals? We want to make sure we also know how to use combinations to find that one. All right, let's look at the last set of problems here. This time we have a 10-person committee, and this 10-person committee is being chosen from 11 women and 12 men that are available. How many different 10-person committees are possible if the committee has, first off, equal representation? And by that, what we're saying is we want to have an equal number of men and women. So 5 men and 5 women, for example. All right. Well, what would this look like? So first off, let's calculate the number of different ways we can choose 5 men from the 12 that are available. So if we want to choose 5 men from the 12 that are available, this would look like 12 choose 5. Now let's look at the number of ways we can choose 5 women from the 11 that are available. Well, that would be 11 choose 5. And what we're going to want to do, just like we did with the fundamental counting principle, is we want to count the number of ways we can choose 5 men from the 12 available, count the number of ways that we can choose 5 women from the 11 available, and multiply those together. Well, this would give you 462 times 792, and so we actually have a total of 365,904 different committees. And let's go ahead and box that. Okay. So I'm going to do one more now, and then I'll give you a moment to try the other ones on your own. So let's look at this one. How about a committee where at most we want 2 men? For whatever reason, we want to have at most 2 men in this 10-person committee. Now, before you just quickly just say, oh, I want to choose 2 men from the 12 that are available, it's actually a little bit more complicated than that. Because in this situation here, there's a couple of actually scenarios here. What you could have is you could have 2, and I'm just going to abbreviate here, 2 men and 8 women comprising your 10-person committee. Or you could have 1 man and 9 women, because the problem said at most 2 men. Or you could also have 0 men and 10 women that are available. The problem just asks for at most 2 men, so we want to consider all 3 scenarios here. So let's go through and calculate each one. So what about when you have 2 men and 8 women? So this part is pretty similar to what we did in the previous problem. So from the 12 men that are available, we're going to choose 2 times 11 choose 8 plus Now, in this next scenario, 12 choose 1. We're choosing 1 man from the 12 that are available, times, again, from the 11 women that are available, we're going to choose 9. And notice, as I'm going through this, every time there's an or situation, we are going to be adding that number of possibilities, or the number of those outcomes and the number of ways that that happens. This would be 12 choose 0 times, remember, and is multiplying. So in case that symbol wasn't clear, this is what I'm trying to write here is and 11 choose 10. Now, if you go ahead and calculate all this, I'm going to just jump straight to the answer. You should come up with 11,561 different committees that are available. Okay, all right. So I'm going to encourage you to go ahead and pause the video and try these next two on your own. And in a moment, I'll just go ahead and write down the scenarios here. So for part C, there was a bit of a typo here. I apologize. This should say no fewer than 9 men. So if this was 9 men and 1 woman, or 10 men and 0 women. So it's pretty similar to the previous problem. So this should be the following. And this comes out to a total of 2,486 different committees. I'll just go ahead and box that. And then if you want exactly 4 men, that makes things a lot easier. We want exactly 4 men and 6 women. So this would be 12 choose 4 times 11 choose 6. And this one comes out to 228,690 different committees. Okay? All right. Well, hopefully by the end of this, you stuck around and you have a pretty good understanding of how combinations work, how they're different from permutations, and how to set up scenarios when we have phrases like at most or no fewer than, or and compare that to situations where we have exactly a certain number of outcomes we're looking for.